Welcome to scheduling and job management number 2, using a cluster effectively. So we're going to go through job submission part 2 and understanding jobs. And the basic part that we haven't covered yet is PBS jobs and memory. The PBS is the portable batch system. It's the scheduling software that we use to run jobs. And it's very important to specify your memory requests correctly. Basically, if you don't ask for enough memory and your job uses more, your job will be killed. If you ask for too much, it will take much longer time to schedule a job, and you will be wasting resources. If you ask for more memory than is available on a cluster, your job will never run. The scheduling system will not stop you from submitting jobs such as that, or even warn you when you do so. If you don't know how much memory your jobs will need, what you should do is ask for a large amount on your first job, and then look at the output of the check job -v, job ID command, or the qstep -f, or potentially the email output that you get when your job finishes. And along there, along with a lot of other information, you should see how much memory your job used. Also, if you don't specify any memory then your job will get a very small default amount of memory, which is 256 megabytes on Jasper. So please ask any questions if they're needed. Another part is please always ask for slightly less than the total memory on your node, as some memory is used for the OS, and your job will not start until enough memory is available. You may specify the maximum memory available to your job in one of two ways. You can ask for the total memory used by your job. That's PBS minus L mem equals, and then in this case it's 24,000 megabyte. Or you could ask for the amount of memory per processor core in your job. So instead of mem, you use pmem. This way, if you run your job with different numbers of cores, and the memory scales with your number of cores, you could just have one number and just change the number of cores that your job uses. So, are there any questions about memory? So in our exercises, we're going to actually have a few examples of it. Okay. So on some systems, we have features and partitions. So sometimes, on some clusters, nodes have certain properties, either a fast processor, a bigger disk, a solid-state disk, a fast connection, or they belong to a certain research group. Such nodes are given a feature name by the sysadmin, or can be given a feature name by sysadmin, so you can ask for those nodes by feature name in your job script. So if, say, you had a cluster with a feature called SSD, you could actually specifically request for it, for a node with such a feature. #PBS minus L feature equals SSD. Partitions are a set of nodes you could specify in your job must run with all of its components inside a partition. To run on a newer node partition on Orsonus, you would, for instance, go #PBS minus L partition equals QDR. So Orsonus has at least a couple partitions, and this is how you specify running in the faster one. Of course, if you do this, and there are empty nodes, empty resources sitting in a slower processor partition, your job will not run there. So whenever you ask for a feature or a partition or basically anything else, you're constraining your job on where it can run. So it's all a trade-off if you ask for something specific. So PBS jobs and GPUs. To request a GPU, use the nodes notation and add a GPU equals X. So in here, we would ask for 2 nodes, 3 GPUs, and 4 processors per node. So there will be 3 GPUs in each node. So modern torque scheduling programs recognize GPU as a resource, and they contain the state of the GPUs. So they won't allow you to won't allow your job to run on a node if the GPUs aren't working on it. It actually manages it quite well. So there's also software licenses and genetic resources. Sometimes not only cluster hardware is required to be scheduled for a job, but other resources as well, such as software licenses or telescope and other instrument time. So to request a generic resource or a license, you could do #PBS -L software equals, in this case, MATLAB :2. So this gives us 2 MATLAB licenses. And you can actually see software licenses and generic resources by typing in the command job info -n. So for instance, on this node, we just actually have one. In this case, we have an SAS license set up here. But if we go to Jasper, there is a large amount of different licenses available. So this is, if your software needs a specific license to run, say MATLAB, it's to make sure that there will be actually enough of those licenses available with your other resources when your job starts. So you won't be in a position where you actually get enough compute cores and memory, and then find out that somebody else has checked out all the MATLAB licenses. So it's very nice that the scheduling system takes care of this as well. So basically, here's the table of all these requests, where you can specify the memory, both by total and by per process. You specify features, partitions, another way of specifying features is also specify GPUs. And it's also possible to actually specify specific nodes if you so desire. It's actually very inefficient to do this, but you can do this. Okay. So now we are at question 17, jobs in memory of our worksheet. And we will continue until question 21. If you are finding that you're having a difficult time catching up, it's also possible for you to just run the answers. You won't gain as much just by not doing it yourself, just by running the answers, but you will be able to see the differences and how it runs. Are there any questions? So here's the link to all the materials. If you follow that link, you'll see the presentations, go into scheduling, and then the worksheet. If anybody has a question, please ask. Either by unmuting yourself or into the group chat. If anybody is done after question 21, please type into the group chat that they're done. If anybody is done, please say so in the group chat. Okay, we're going to start going over questions 17 through 21. So you're supposed to, in question 17, start with the startmem.pbs. All this job does is it asks for 4 processors. It lasts for 2 minutes. It sleeps 60 seconds and writes out the host name. Now, the correct answer to question 17 is you're asked to set up a PMEM of 12,000 megabytes. Just put it in right there. And when you actually look at the output of our commands here, showQ just shows you that it's running. usenet-a shows you that it uses 12,000 megabytes, but doesn't actually tell you 12,000 megabytes how. Check job on the other hand, actually tells you how much memory it uses. It's using 11 or 12 gigabytes per core. That's why it's allocated to 2 separate nodes. Because these nodes that we have, they don't have enough memory to run the entire job, requesting 48 gigabytes in one node. So they have to use two cores on one node and 2 cores on another. When we look at question 18, we run the same job, but this time, instead of using a PMEM of 12,000, we ask for a MEM of 12,000. And when we look at this job, we see that it runs 4 tasks by 1 processor and 3 gigabytes of memory in each task. In other words, 4 processors, each with 3 gigabytes of memory. And this time it can run on a single node. So there's a very big difference between MEM and PMEM. And if you select the wrong one, your job may not run, because there may not be enough resources available for your job run, or it may take a very long time for your job to start. And in question 19, we basically ask for PMEM of 3,000. The results should be very similar to the results of question 18. And yes, it is the same result. So question 20 is actually a really interesting one. In this case, you're given a program I decided to call cryptic, just because we don't know what it does. I actually don't know very much what it does. I actually asked somebody else to write this. And we don't know how much memory it uses. So we need to make a guess about how much memory it uses. We guess very, very high, but not so high that there is no resources available on the cluster. We run this job, and then we lowered the amount that's needed. So if you run this a few times, or if you looked at the output of your email message, you would see that you could actually run it with 3,000 megabytes or 3 gigabytes of memory. Now, you don't want to guess too high, because you're using more resources. It's more difficult for your job to be scheduled. Those resources that you use are going to be taken into account on what your priority is. So you want to use exactly or as close as you can, but higher than the amount of resources that your job needs. So that's basically the correct answers. You need to try it once, use a higher amount of resources, higher amount of memory, and then lower it back down, especially if you're running a whole bunch of very similar jobs. You need to have an understanding of what type of jobs you're running. And actually, if we do a check job minus v, we could actually see how many resources are being used. That group in qstat minus f. Yep, qstat minus f. And here we see that we're using slightly less than 3 gigabytes of memory per core. The other way is you could read the email output that you get when your job finishes or crashes. Or question 21. You were asked to run asking for 2 SAS licenses. So here's the answer. Pound PBS minus L software equals SAS colon 2. This will use
Welcome, Youssef. If you could please mute your microphone, there's a lot of background noise coming through. And to do that, you can click the microphone button. Thank you.
So that's memory features and software licenses. So we're going to continue on. So job submissions requiring full node. So sometimes there's a need for exclusive access to guarantee that no other job will be running on the same nodes as your job. So this is if you are trying to debug and nothing is working, and you think that maybe other people running on the same node are causing the problem. Now, you can guarantee this, but if you do set these, your group is going to get charged for the whole node usage, not just the resources that you requested. And that's going to go towards your future priority. And it may take a long time to gather the resources needed for these jobs. And of course, this means that there's resources that aren't being used by you, which are going to be wasted. Now, this is basically typically only used during debugging. Sometimes you need to guarantee a pristine environment. Now, to guarantee that your job will only run on nodes with other jobs of your own, you could do a PBS minus L n access policy equals single user. To guarantee that your job will run on nodes with no other job, you do an access policy single job. You can also guarantee that each core of your job will run on a separate node with nothing else running on that, and that's n access policy equals single task. Now, this is basically only for debugging purposes. But if you are trying to run software and debug it, and nothing else is working, this may be a way of doing that. It's going to have unfortunate implications for you and your priority later on, though. So it's not recommended you do this if you're not debugging. So when we're talking about running jobs, you're usually in one research group But it's possible that you're part of two separate WestGrid projects or research groups, and you are running jobs for both. Well, in that case, you need to specify the accounting group for each project so that the correct priority and the accounting is done for each job, and so it is charged to the correct group. In order to specify an accounting group, you would use this formula here, pound PBS minus capital A, and then the accounting group. You could find more information about your accounting group's RAPIs on the WestGrid accounts portal, also the CCDB. You could see your accounting group information with the job info -a command. Now, it's not going to have very much here on this little test cluster that I have. On the real cluster, you would have access to a lot more information. Or at least it will have your actual usage of that cluster, not just what you're running for testing purposes here. Okay, so here's another more advanced topic. It is, what if you want one job to start after another one finishes? So, for instance, Jasper has a maximum wall time of 3 days, 72 hours. But let's say you have a job that needs a couple months to run, but it could restart from the last place it left off. So it writes its output. You could break it up into smaller pieces. Well, if you do that, then, and people often do this, they try to run one job, get an email, try to run another one. That's not really that efficient. What you can do is you could actually use a job dependency. So if you want one job to start immediately after another one finishes, or at least have that ability, use a job dependency. qsub minus w depend equals after OK. So that means that after the first job finishes and everything's OK, the second one can be run. You can break apart your longer jobs this way. So you take in this example, you're taking the job ID that's generated by the qsub command, and you're using it to run the second job as a dependency. If there are any questions, please speak up, or please email in the group chat, or please send a message in the group chat. So other interesting things that you can do is prologue, epilogue, and data staging. So prologue is a script that runs before your job starts for a maximum of 5 minutes. You could actually set a script to do that. -l prologue equals. Epilogue script runs after your job is finished for a maximum of 5 minutes. These scripts are nice if you need to document some more information about the state of your job in a scheduling system. And jobs can resubmit themselves with an appropriate script in the epilogue on some systems. So some people write scripts that if the job doesn't finish and it's shutting down, to resubmit itself and restart from its last place. So here's a sample epilogue script. There's a whole bunch of variables that are available to epilogue, such as the job ID, the user ID, the job name, the session name, the list of resources used, and so on. As well, temporarily available local storage. So some software, like Gaussian, needs to write and read very small files, and a lot of them, to the disk. So the cluster file system is not very good. Neither is NFS, this type of usage. Basically, Blaster does not like small files being written and read. It's not very high performance this way. It likes large file I/O. So if you do this with Lustre, the whole file system on the cluster will slow down, and you're not going to get very good or almost any performance out of your job. For this purpose, to deal with this, each node has a local disk that is shared by all the jobs running on the node. Sorry, we have a question. It's if you have an epilogue script and mail requested in your PBS, does it stop the epilogue from running? No, it does not stop the epilogue from running. Yeah. I am guessing that that last line was cut a little bit, but that should all be one line, right? The epilogue should say pound PBS minus L space epilogue. Yeah. And then it should run normally. So you should get both the epilogue and, oh yeah, it must have run permission. So it's a script, right? It's just like any other thing you're running. So yeah. Also, you should have it probably write out somewhere its information. Yes, those permissions should be correct. You basically need execute permission to act. And it has to be owned, of course, by you. Or you have to have execute permissions for the epilogue script that correspond to your username. So if it's owned by you, then the permissions that are in the group chat are correct. Okay, going back to our temporary local available storage. So each node has a local disk that's shared by all the running jobs on the node. So you could specify the local storage request via PBS minus L file, and then how much space you want to use. There's a directory created for each job when it is run. When a job is finished, this directory is automatically erased. The directory name is tempter here. So an example of using temporary storage is your first request for at least 1 gigabyte here, with pound PBS minus L file equals 1,000 megabytes. You change the directory to the temporary directory. You run your job. You then make a directory in your home directory, and you copy the output. So if you don't do this, if you just let it finish, then that temporary directory will be deleted. So if you don't care about the files because they're temporary only when your job is running, then that's fine. But if your output is there, you want to save your output. So it's very important that you know what you're doing here when you're using temporary available local storage. And here we are with all the different PBS script commands. I also listed our environment variables again. Remember, you could make use of these in your job. So we could break for practice. We're going to be doing question 22 through 28. So this will be a lot quicker because we don't have very much time. You may want to just run the answers and look at the answers. We're a bit short of time, and we're going to have to continue really quickly. So we have a few people running their jobs. You see in this example, for answer 22, that this job is running all on node 228. And if you actually check the node, now this is a sysadmin command, we can see that there's only one job running, because that's exactly what was asked for. And my job is running on node 226. Now, in question 23, we're asked to do something slightly different. We're asked for this job not to run on any nodes with any other job. So previously, it was possible for my job to run on a node with other jobs of mine. But if we ask for an access policy equals single job, that will no longer be true. And we see I'm running on node 225 with 4 cores. And that other jobs aren't running there at all. In question 24, we're asked to do something rather silly. We're asking for each core to be run on a separate job, or on a separate node. So that's an access policy equals single task. When we do a check job, we see that there's one core allocated on 4 different nodes. And if actually, see, there's more than a few people running, so all the nodes have something running on it, and we've told all the nodes that don't run any other jobs on those nodes. So although we have a large number of cores still available, 92, we still have a new job that can't start until some of our jobs finish. So this wastes quite a few resources. It's useful for debugging only. For question 25, we're asked to submit a serial job named dep1 that has a wall time of 2 minutes and sleeps for 120 seconds, and submit serial job 22b, or waits until job dep2. Dep1 is done, yeah. And basically, our script here just runs and submits the PBS script Q25.1, and then sets that and starts a dependency on the second job. So we can see the jobs. We have a job 2503 and a job 2504. And one of them is running, and the other one is actually in hold state. If we did a check job, we will see that this job cannot run. There's job dependency on job 2503. Job successfully complete has not been met. So job 2503 has not run. Therefore, job 2504 will not start. So this is how you do job dependency. So for question 26, epilogue. We have epilogue.script, which is basically what was there in the PDF. And we ask to run the epilogue script. And our job has finished. And in the output here, we have the eplog argument. So we actually show us how much memory this job has used, along with all the resources that were asked for. The wall time of 2 minutes, the default amount of memory of 256 megabytes, and the fact that it uses one processor. So this would be an example of an epilogue. Notice that this output runs after the output of the job itself. In that case, it was just the post name. So question 27, it's about using temporary directory. So submit a job that runs in a temporary directory and uses no more than 1,000 megabytes of space. Here we have it. We ask for 1 gigabyte of basically space with -L file equals 1,000. We change to the temporary directory. We actually here, I just echo hello world into p17.out, and then I just copy it back into the directory I'm working from. So in a few minutes, it's going to finish. Actually, since I have the sleep at the very end, you can actually already see the P17 output already. It's hello world. So here's an. So you did see that we actually did write it out into the temp directory and then copy it over. So we made use of a temporary space. So in question 28, we're asked to submit a job that prints the queue that the job was run in. So in this example, we can go through our PBS commands and look at our PBS environment variables. And we find that #PBS_Q is the job queue. So all we do is echo that out. And it'll take a few seconds to run. And in a few seconds, this job will complete. And we'll be able to see. Taking a bit longer. For this job to finish. And there's something. Sometimes there's as much as 30 seconds extra for the system to clear the job. As we see, there's no error. The job output shows that it was in queue batch, which is actually what we saw when we did qstat -a. So you can actually take out any of these environment variables. This is how you get them out into your job output script. Okay. So I apologize once again for these short practice sessions. Unfortunately, we only have so much time to go through all the material. So now we're going to go with getting information on your job. So we've been running some of these commands, and I want to go in a little bit more in depth in what you see in these commands output. So there's a list of tables of these commands. And we'll go through them one by one. So job info. Job info is a WestGrid script, and it gives you a lot of information specifically for you and gets rid of a lot of extraneous information, information that you don't need that much. So if you do a job info -j, you can see all your jobs, which are running and idle, how many processes they use, how long their maximum wall time is, and which class or queue are they in this case, batch. The qstat -t command, the -u user just limits it to you, but the -t is the one that shows you all the array jobs. So in this case, you see both the main job ID as well as the array ID, each part of it, so you can see that some parts are running and some parts are queued. In this example, you also see, who it belongs to, which queue is it in, how many cores it's been using, and so on. How long it's been running, and how long it can run for. qstat -a, on the other hand, just gives you the information for the jobs themselves. And in this case, if you don't have a -u in your username, you see all the jobs there. So mine, as well as some of my colleagues here, jobs. There's Terry's job, and other people. And you see which queue they're running in, how much resources they take, how long they're supposed to run, and how long they've been running already. qstat -r only contains information on running jobs. So once again, it's the job ID, who it belongs to, its queue, the job's name. Notice the job's name is different from the job ID. There's a session ID if it's actually running, which in this case it is with -r. How many resources it takes, and how long it's supposed to run, and how long it's been already running. Show queue. So Show queue is yet another command. Show queue is command from Moab. So usually these scheduling systems are running two pieces of software. Moab that actually decides which job will run, as well as Torque or PBS server, which takes care of actually running the job. So QStat tends to be the command for Torque. ShowQ is the command for Moab to see information. Moab commands tend to be a bit slower because they could get overloaded. The scheduler is really, really busy. So we see active jobs, the jobs which are running. We see its state, the running jobs. We see how many processors they're using, how much remaining time, and when was the start time. Here we see that 640 of 2,048 processors are in use by local jobs. But there's 4 active jobs running. So about 31% of this system is actually being used. There's also an eligible job, so this job can actually be run. So we see its state is idle. It's eligible to be run. It wants 256 cores for 12 hours. And it was queued on April 10th. There's also block jobs. So block jobs are jobs that cannot be run. Now there could be many reasons why they're blocked. One of those is because you have a job dependency, and it's waiting upon your job dependency to finish. Another one is that the system tried to run it and failed. So that's deferred state. So in this case, there is one deferred job, which was also submitted on the 10th of April. So there is a show queue minus B. It's showing you, the blocked jobs, and it actually tells you why they're blocked. So you may have some jobs which are, say, idle. These type of jobs tend to be blocked because you're running a lot of jobs already, and you're only allowed to run so many at one time. So any additional jobs will be blocked. Also, the scheduling system will only consider your 5 top jobs every time it's running. Everything else will tend to be idle, but still blocked. There'll be jobs in batch hold. Batch hold basically means that the system tried to run your job and it couldn't, it has failed, and it's not going to try anymore. So these jobs right here, they'll no longer be tried to be run. There was something wrong with them that the scheduling system could not run these jobs. Jobs which have a deferred. These deferred jobs, the scheduling system tried to run them, failed, but is still going to try. So depending on which system, but it's usually something like 12 or 24 tries. And after that, it basically says, nope, it gives up. It can't figure out how to run this job. It crashes every single time. Here's a good one. Show queue minus I, or job info minus I. It tells you the priority of your jobs. So your priority can be positive or negative. In this case, this job here in red, Masao Fujinaga's job, is actually the highest priority job in the queue. There's a few other jobs. These ones belong to me. And then there's also negative priority jobs. So the system will actually go through the jobs and schedule them in order of priority. And if you want to see the current priority right now of the current jobs that are eligible to be run, you could do a show queue minus I on a cluster. And I'll actually tell you that. We'll answer how the priority is calculated and where it comes from, and how your usage affects it, and your allocation tomorrow. So there is a qstat -f command. So this qstat -f command, it actually gives you a lot of information about your specific job. You have to put your job ID. It tells you your job name. It tells you also the owner, the job state, in this case queued, the queue that is in parallel queue. It tells you the error path where it's going to write out the error message. It's going to put down any job holds that it has, whether it's supposed to email you, what the email address is, the output path for any output, the job's priority, how many nodes and what processes are needed. So in this case, 1 node, 12 processors per node, how much memory per process, how long the maximum wall time is, in this case 3 hours, as well as any arguments that we've submitted with. There's also a lot of other information, but these are the really important ones that I listed. Check job, on the other hand, is the MOAB version of the same command, pretty much. So it gives you the state of the node, of the job. In this case, it's idle, its name, who it belongs to, which group, which accounting group, which class or queue it's in. Its wall time. So this job is idle, so it used 0 wall time of its 3-hour maximum wall time. When it became eligible to be run, and when I submitted it, in this case, it's pretty much the same time. It tells you also how long it's been queued. You also gain some priority for the job sitting in the queue. So in this case, there's 20 minutes of queue time. That causes your job to gain extra priority. We'll talk about that tomorrow, I believe. So it requests 12 cores, and each core requests 256 megabytes of memory with it. It has an ID of 508. In this case, it actually emails me when the job starts, ends, or fails. And we see its priority. It's negative 88,787. So this is basically how you read the check job output. Are there any questions? Okay. So let's look at the check job minus V minus V. So if you add 2 V's, you get much, much more detail. Once again, you get the same detail that you had before, who the job belongs to, what its wall time is, what its state is, and so on. But you get a lot more information as well. How much resources would be dedicated per task? So 1 processor, 2 gigs of RAM, 2 gigs of swap are available. The node set. So sometimes you can use features and node sets, so it tells you this as well. It tells you when you're supposed to be notified. In this case, it's only job failed. It tells you the output information, how the job was submitted. In this case, there was some submission arguments with the job, its start priority. And then it tells you why it's not running on every single node. So most likely because there are some other jobs which are running, or a node is reserved, or doesn't have enough memory, empty, or it's busy, and then it doesn't have enough cores available, and so on. So at the very end, you'll get a message that says, job can't run because there's not enough resources available currently. Also, it tells you here that it violates a max iJob limit of 5. In this case, the scheduling system only checks the first 5 jobs, and this isn't one of those, so it doesn't even check, really, this job. Yeah, so I'm going to run some of these commands. I don't have any jobs running either way. But if you look at a cluster, there's tons of jobs. A lot of them are running. And so on. We'll run a few jobs. And we see that the state of this job is running. It's running for 5 seconds out of 2 minutes. You can actually see which nodes are allocated. So node 229, there's 2 cores allocated on it. You can see that it uses 2 tasks, each with 1 core and 256 megabytes of RAM. We can even see where its output and error files are. And its start priority. In this case, a very negative 887,195. That's because I've been running a lot of test jobs here on this cluster. Show Q minus I doesn't show anything. Show Q minus B doesn't show anything because we don't have any block jobs. However, if we rerun those 2 jobs, you can see 1 block job. And that's the job that is being held. So I just run the question, run the answer for question 25 again. And once again, it's being held. There's a hold in place. Now notice show Q minus I doesn't show it because it only shows eligible jobs. So a block job is not eligible. You can't even see its priority unless you're its owner. You can run Q step minus F. On my job here, we see that it's being held. And it's going to run after job 2512 exits with OK. So it doesn't error out. If that job crashes, this next job will not run. We could see all kinds of information, how much memory it's requesting, what the submit arguments were, and so on. Where I submitted it from. So this is basically a demonstration on a cluster. And now we go and do question 30. Yeah. No, sorry, 29 and 30. So basically, it asks you to run some of these jobs and run some of these commands. Also, if any of you have questions, please state them. You may want to run some of the jobs from some of the earlier examples. So are there any questions? And if you're done all the questions up to question 30, can you write down done in the group chat? Okay. So this is pretty much the end of our second part session. Tomorrow we're going to be doing third part. Now there we're going to actually concentrate on getting more information on the cluster, some more things that are specific more to the cluster than they are to the job, such as cluster limits, reservations, and topology. As well, we're going to talk about priority, where it comes from, how it's given, how Compute Canada rack allocations work, and how the formula for priority called fair share works. And how do you get it? How do you how can you use most effectively and get as much work and jobs finished to be run? Also, we're going to take all this information that we've learned over the past, well, yesterday, today, and tomorrow, and we're going to use it to troubleshoot, to see what's wrong with the job, see why it's not running, to determine if there's a problem with the job, with priority, is the system busy, that sort of thing. So that's going to tie everything together. So I really suggest you guys show up for the next session. As well as that, on October 4th, we're going to be having office hours. So there, it's going to be me, Masao, and Erming. So for the last 3 sessions, we're using WestGrid for scheduling and so on. And if you run into problems, or if you are trying to implement some of what you've heard here and want to have some more questions, we'll answer them on October 4th as well. Yeah. So are there any questions? I apologize for rushing you guys through one of the earlier ones and then having extra time at the end. I was not sure how long that was going to take. So see you everybody tomorrow at the same time again.